Hey guys, today's lesson is a really short lesson on the properties of different types of compounds. So in our naming lesson, we talked about how there's acids and bases as well as ionic and covalent compounds. We're going to be looking at how each of those different categories have their own unique properties and kind of what that means for the different molecules. Okay, so we're going to be going over acids, bases, ionic, and covalent compounds. We'll start with the properties of acids. And just a reminder, you can tell that something is an acid because its formula starts with an H. All acids will taste sour. They're also corrosive to metals as well as other material like organic material, which is like living things like your skin. They have a pH less than 7. They produce hydrogen ions in solution. That's the H at the front of the formula will essentially dissociate from the acid and go into the solution. All acids also neutralize bases and they conduct electricity when they're in solution because of the fact that they break apart into ions. Bases, on the other hand, can usually be identified because they have an OH at the end, though ammonia, NH3, is an exception to that. Bases will taste bitter. They are also corrosive to organic material, like your skin, but they're not corrosive to metals the way acids are. They will have a pH greater than 7, so up to 14 on the pH scale. They will produce hydroxide ions, which are OH negative ions, when in solution. They will also conduct electricity in solution, just like acids do. They will neutralize acids, and they tend to be very slippery. So part of that is because when they dissolve, say, your skin, they actually kind of turn your skin into soap, which is slippery. Then we'll talk about covalently bonded compounds, also called molecular compounds. So these are ones that are 2 or more non-metals bonded to one another. They tend to have fairly low melting points, so it doesn't take a lot of heat to melt them. They don't hold a really rigid crystal structure very well. They also tend not to conduct electricity because they are not made of ions, so there's no charge within them. They can be polar or non-polar. And so when we're talking about polarity, essentially what that means is that there is an unequal sharing of electrons in the bond between the different atoms of that compound. So this happens when one atom of the compound has a stronger pull on the shared electrons than the other compound. And we can determine polarity based on the structure of the compound. For this year in grade 10, you need to know what polarity is. So it's the fact that you have an unequal sharing of electrons in a covalent bond, and that it happens because one atom is pulling more on the electrons than the other. You should also be able to identify what side of a molecule will be slightly negative and what side will be slightly positive. But you don't have to just know if a molecule is polar or non-polar. We'll get into that in Chem 20. So let's look at an example of this. Okay, so when we're talking about polarity, what we're really talking about is the electronegativity of different elements. And electronegativity just refers to how strong of a pull they have on electrons. And the general trend is that as we go up and across the periodic table, from francium to fluorine, we increase the electronegativity and therefore increase the pull of electrons. So what that means is that fluorine up at the top here has the strongest pull on electrons because it has the highest electronegativity. And so the closer an element is to fluorine, the stronger its pull will be on electrons. So knowing that, if I draw, say, a water molecule, so H2O, which would look like this, because oxygen is right next to fluorine, it's going to have a stronger pull on electrons. So any of the electrons, the 2 electrons that are in this shared bond here, are actually going to get pulled towards the oxygen and spend more time with the oxygen. And that makes the oxygen end of this atom slightly negative. And this little kind of curvy D is our term. It's like a Greek letter, but we use it to represent slightly. So it's slightly negative, and the hydrogens are slightly positive. And so this end or pole of this molecule has a different charge than the other end or pole of the molecule. Because it is a polar structure, the electronegativity of oxygen is higher than hydrogen, so it is hogging the electrons in that bond. And the last type of compound we're going to look at is the ionic compounds. So that is when we have a metal bonded to at least one nonmetal. They tend to have really high melting points. It takes a lot of energy to melt an ionic compound. They also tend to keep a crystal shape. Ionic compound structures are called crystal lattice structures because they tend to hold that crystal shape really well. They do conduct electricity in solution because they are made of ions, unlike molecular compounds which don't conduct electricity because they're not made of ions. Ionic compounds are soluble in water, so they dissolve in water. And the reason for that is because water is polar, which we were just discussing. The slightly negative and slightly positive ends of a water molecule actually attract the positive and negative ends of ions in ionic compounds and can pull the ionic compounds apart. Ionic compounds that dissolve really well are called very soluble. If they don't dissolve very well, if only a little bit of them dissolve, then they're considered slightly soluble. And you do have to be able to predict whether an ionic compound is very or slightly soluble based on a solubility table. So let's look at how that would work. Okay, first, just to go back to our water molecule for a second. So if we had, say, some sodium, so Na bonded to a Cl, the sodium would be positive, the chlorine would have a negative charge. And so because of that, there would be an attraction between the negative pole of the water molecule and the positive ion, and between the negative ion and the positive pole of the water molecule. And those different attractive forces would actually pull apart the salt molecule. So that's why ionic compounds dissolve in water. Now, this is what your solubility table looks like. And the way that we would use this is we would first find the non-metal in the ionic compound across the top in this kind of darker column here. And then we find the metal in this bottom section. So if we were looking at NaCl, for example, we would find the chlorine ion first, and then we would look underneath it to see where the sodium ion fell. And because the sodium is not listed down here, it falls into the most category. And anything in this top column is very soluble. If we look at another example, let's say calcium hydroxide. So that is CaOH2. Let's write that out. So calcium hydroxide. We would start by finding our hydroxide ion across the top because it is a non-metal. And then we would find our calcium ion underneath it. So hydroxide is right here. Then I would look and see, is calcium listed? And obviously calcium is not any of these. Calcium is also a group 2 element, so it's not included in this group 1 here. It is a group 2 element, and therefore it falls into this category down here. Calcium hydroxide is therefore only slightly soluble. We could also do the example of let's say silver bromide. So silver bromide is AgBr. So we would find the bromine ion first, since it is our nonmetal. Then we would find our silver ion, since it is the metal. So bromine is right here, and then we look underneath, and silver is listed as one of the ions down here, so therefore it is slightly soluble. Okay. That's really it for today's lesson. Like I said, it's a nice and short one. Let me know if you have any questions.